Okay, so welcome everybody. Thank you for being here, and thank you, for accepting to give a seminar in the Hitchhiker's Guide to Rheology webinar series. So yeah, today's speaker, as you can see here, is Ambre Bouillant. She's a CNRS researcher at MSc lab at the Université Paris-Cité, so in Paris, France, and she's going to talk about nucleation and condensation on soft gels. So with that being said, again, thank you for being here. I leave the floor to you and to the people here today. If you want to ask questions, as always, just raise your hands or write the question in the chat. And Amber already agreed to answer the questions while presenting her work. So yeah, please go ahead.
I think I will try to share the screen.
Yeah.
Masking. No, I don't know. Oops. I do?
Yeah.
No. Okay. Yeah. Okay,
It's
good.
great.
So thank you very much, Michelle, for this introduction. Here we are, and thanks a lot for this invitation. So I think the seminar series is amazing. So I'm really glad to be part of it. So you can all see my screen?
Yeah.
Okay. Perfect. So I've been asked to present a bit my research interest and my past, my trajectory. So I did a PhD in soft matter physics and fluid dynamics in École Polytechnique. So I was working with David Quéré and Christophe Clanet, studying the Leidenfrost effect. So when you put a water drop on a hot pan, so the water drop can levitate on a cushion of its own vapor, and it has a very rich and interesting spontaneous dynamics, but also forced dynamics. And then I decided to move for a postdoc, and I went to the Netherlands to work with Jaco Snoeyer. So I wanted to work a bit more to bring a bit some theory in my work. So Jaco Snoeyer was the expert in capillary, but also elastic problem. And I think it was actually bringing two topics that I like quite a lot, and that I think is also something that rheologists like when material behave half as liquid and half as a solid. And there I started to look at so capillary singularities in presence of polymer chain. So I look at pinch-off, coalescence, and spreading of viscoelastic drop, how they are affected by the presence of viscoelastic polymers. And then I developed as a second part of my postdoc, actually, I started to work on soft gel, and in particular on condensation on soft gel. And this is actually the topic of today's talk. So really, if you have any question during this talk, feel free to interrupt me. I would be happy to answer. Okay, so condensation refers to the transition of vapor to a liquid state, and this actually occurs when the humid air is cooled down below the dew point. That is when we cross this curve from right to left in this pressure temperature diagram. And this is something that is really known. For example, when the exhaled air just condensate on your glass. And but it can also be exploited in nature, either by human or by insects to collect water in deserts. So human usually they use a textile fog collector to really capture the liquid, while on this little beetle back, you can see that it is covered by a very intricate pattern of alternating hydrophilic and hydrophobic region. And this very intricate tailor-made covering enables this beetle to collect water from the early morning fog and to survive to dry environment, deserts. So condensation, from what we see on those examples, is known to be highly sensitive on the substrate nature, and especially on the chemical and nature and the presence of heterogeneous defects. So for example, on rough and solid substrate, we know how it works. So nucleation is promoted by surface defects. So the surface defect, whether by their shape or by their chemical nature, can reduce the energy barrier to nucleate a new drop. So as a consequence, as you can see on this picture, is that the breath figure, so the pattern led by the droplet, reveals directly the heterogeneity of the surface. You see the scratch. So the number of defects is actually reflected by the number of drops. If I play this movie, we can also see that condensation unfolds in several phases. So first of all, right after cooling the substrate, droplets nucleate at a nanometric scale. Then they grow and eventually merge with their neighboring drop when they come into contact. So coalescence leads to polydispersity, in particular because by freeing some space between two droplets, it enables a secondary nucleation in between existing drops. And this is what we see here in the spacing between the drop. Now, there is another category of substrate that has been widely investigated, which is condensation on atomically smooth viscous layer. So here what we see is that when you cool down the substrate, all drops seem to appear simultaneously, and they do not coalesce since they are completely stuck here in the oil layer. So they cannot move somehow in the liquid, the viscous liquid. So breath figures are very regular in the end and highly monodisperse, which can be conveniently used to pattern substrate. And this is an idea that has been developed by a bunch of people, where they actually solidify the polymer viscous film with UV light or by evaporating its solvents. And then by evaporating as a second step, the collected dew droplets. So in those applications, it is really important to control the condensation dynamic. And it is quite complex because the substrate is solidifying. So it's neither liquid, neither solid. It's really time changing and in between. And the question is now how the surface rheology affect the condensation process. And this is something that I will try to answer in this presentation. So what interests me is actually substrates that have properties that are lying in between, that are neither liquid, neither solid. And those typical material have been quite investigated. For example, people have looked at what happened when you do condensation on liquid infused surface. And what we see is that the condensation seems to be enhanced, eased. Since the drops are highly mobile, it's very convenient. You can just tilt your substrate and harvest your liquid. Other people have looked at PDMS gel, condensation on PDMS gel. And there was the Circular et al. Were the first to notice that condensation seems enhanced on soft substrate. So if you continue the dynamics, they were actually observing that on relatively stiff PDMS, you could observe a bimodal distribution of droplets. And so my motivation was actually to characterize in detail the dew formation on soft PDMS, ranging from highly, very, very soft, almost liquid-like, to very stiff PDMS. Okay, so how? So I perform condensation experiment on a reticulated polymer network in pink that I cool down in a chamber with controlled humidity. And the PDMS that I prepare were prepared by mixing a prepolymer with a cross-linking agent. And by adjusting the ratio of those two components, we can vary actually the elastic modulus G from 100 Pascal to 1 megapascal, keeping the same surface chemistry. A droplet deposited on such a substrate can actually exert a capillary traction gamma, which results in the formation of a ridge with amplitudes that scale with the elastocapillary length, gamma over G. And in my experiment, the elastocapillary length is varied by, from 100 nanometer to 100 micrometer. Okay, so let's first see what we get on the simplest case, so the most rigid PDMS case. So on rigid case, when I start to cool the substrate, there are about 100 droplets that nucleate and start to grow. And then, well, first independently, but then by coalescing. And the number of drops is decreased significantly. The droplets get bigger and bigger. And we see that after more than 1 hour, the droplets cover about 60% of the gel surface. In contrast to what we get on regular solid, we see that there is almost no formation of additional nuclei in the dry region between the drops. Here you see that everything is clear. There are no small droplets in between. Okay, so this is almost, classical case, except that we do not see secondary nucleation. And now if I look at what happened on a soft gel, we see that the behavior is clearly different. So I'm gonna pause this movie. And the first thing that we see is that strikingly, there are much more droplets that nucleate. Second thing that to notice is that the elastic capillary ridge that I presented previously tend to attract droplets together, to gather droplets together, leading to the formation of cluster of droplets. And those clusters exhibit a certain asymmetry. We see some elongated chains, but surprisingly, they do not merge, the droplets do not merge. I'm gonna play this movie once again. So we see that we nucleate, the droplets tend to attract, and we see very few coalescence events. Which actually, in the end, after almost 1 hour of the experiment, what we get is a very original state because we form a bidimensional crystal of droplet with a high monodispersity. Okay, so to summarize a bit the observation and to present a bit the menu of this talk, we see that the softer the gel, the more we nucleate droplets. And I'm gonna quantify this effect and try to tell you how much, how surprising it is. Then second thing that I will present is the reason why we get nearly monodisperse pattern with no secondary nucleation, at least when the droplet enters the optically accessible range of 1 micron. And I will try to explain that. And later, I will try to explain the evolution of the number of drops, so how we can rationalize our observation with a universal coarsening law. Okay, so to study those effects, we actually need to count and track well droplets. And this is very easy on stiff substrate because we see very well separated circular droplets, so the detection is simple. But on a soft case, it's quite it's more subtle. So in that case, I first detect the cluster of drop, and then among this cluster, I look for the dark spots that correspond to the light reflection at the summit of each droplet, and then I segment around it. And from this, I could deduce the number of drop, so the number of drop density, the percentage of the surface that is covered, their individual shape, and size to do some statistics. So let us first focus on the droplet number per surface area. So I denote this quantity as a psi, and I plot this quantity psi as a function of time for different for given humidity and for different gel elastic moduli. So we go from soft in yellow to blue to stiff in blue. So what you can see is that as soon as the droplet enters the optically visible range, psi plateaus at a value that I will denote psi naught, the initial droplet density, and that will eventually decrease after a delay that can be quite large actually. That is about 1,000 seconds for the softer gel. So the height of this plateau can be measured, and we see that it varies greatly with G by about, it increases by 2 orders of magnitude when G is decreased by 4 orders of magnitude. And I have complemented those experiments by reproducing them on first a pure liquid that is uncross-linked PDMS. And what we see is that the number of drops that we get is very close to the softer gel that we were using. So it's very continuous. And then I also reproduce this experiment on very stiff substrate. How I just grafted polymer brush, so PDMS brushes, on a silicon wafer. And so you end up with a nanometric layer that is infinitely stiff. And what we see is that we really have smooth transition from soft to stiff. Just to compare with the data from the literature, they were also getting some initial droplet density close to the one that I measure, although we don't know if they measure it at the very early stage of the experiment or a bit later. Okay, so how can we understand this continuous transition from stiff to soft? And for this, let us first understand why it is easier to nucleate on liquid. So the asymptotic limits in some way. So what sets the energy barrier to nucleate? So this is a theory that is called the classical nucleation theory. And what it compares is actually the energy that is available in the supersaturated vapor with the energy cost associated with the formation of new interface. So on a stiff substrate, if we treat the droplet as microscopic liquid phases, we can actually assume that they have a hemispherical shape, and we can actually write the first term with classical thermodynamics, and then the second term by just like managing some geometry, and we get actually an energy barrier that varies with R, the radius of the drop, and this sets the minimal size of the nuclei, if you want, the size for which the droplet it is energetically favorable for a droplet to nucleate and grow. Okay, so we can do the same thing for a liquid, but in this case, since the substrate is deformable, the drop can sink into the gel, and so the shape is slightly different. So what we do is we just assume that its shape is described by two hemispherical cap, and by managing some geometry, we can also write the energy barrier in a similar way. And what we need now to see whether the energy barrier is higher for liquid is to plug some contact angle. And for this, I did some independent calibration experiment where I measure the contact angle from side view experiments. So on the stiff case, I measure 108 degrees for the upper contact angle. And for the liquid case, I measure an upper contact angle of 30 degrees. Unfortunately, it's very complex to access the lower contact angle. But for this, I just use Neumann's law, which is the equivalent of Young's law for deformable substrate. Okay, so if we plug now those values in the theoretical prediction, we can actually show that, Leah, yes?
Yeah, I do have a question.
Yeah.
Maybe I was not really focused in the model, but you don't take into account eventually some dynamics effect of that. You cannot have any velocity pressure whenever it comes to
yeah. So this is really a thermodynamical picture. Actually, it's just to look at the energetics of this system, to see whether you will have thermodynamics that will drive the nucleation and growth.
Mostly.
But then for the dynamics, I completely agree that the drop will grow, and then it will have to carry its reach and its deformation in the gel. So for the dynamic, it's something more subtle, but here it's just to compute the threshold radius upon which we should see droplet nucleating.
Yeah, I see. Okay. So yeah, this graph actually, I needed it for you. You can continue. This is exactly.
Okay. Very good. Thank you for the question. So here you see that the energy it gets a maximum for a radius that sets actually the minimal radius at which droplet nucleate. And what we see on this plot is that if we compare the red solid line to the liquid, the blue liquid line, we actually see that the energy barrier is lowered by a factor of 2, roughly, while the size at which droplet should appear is also decreased by a factor 2. Okay, and from CNT, what we know from the classical nucleation theory is that the nucleation rate, so the number of droplets that must nucleate over per unit time, is treated as an activated process, an energetically activated process with an energy barrier delta G star. And so psi naught is expected to scale as exponential of this energy barrier. So a factor 2 decrease would sensitively affect psi naught, the initial number density. So qualitatively, this explains why it is easier to nucleate on a liquid than on a rigid substrate. However, what it does not explain at all is that, first of all, the plateau in psi that we were observing previously suggests a constant, that the rate vanishes, while this theory predicts a constant nucleation rate. So we should see droplets appearing with a certain constant rate over time. The second thing that it does not explain is the order of magnitude in the delta G, because you get energy barriers that are about 1000 kT, which is like unphysically huge. If you plug this back in the exponential, the Boltzmannian exponential, then you get a nucleation rate that is completely vanishing. So the CNT predicts a vanishing nucleation probability. So this is quite puzzling. And so this is actually something that is very common in the literature, that the CNT is failing. This is a theory that only works like qualitatively, but that makes some very strong assumption. For example, it assumes that the drops are at equilibrium, and also that they have a macroscopic, the shape that they would have if they were macroscopic. And here, for example, if I assume that the angle theta prime below the horizontal remains equal to 0, so meaning that the droplets do not have the time to sink into the gel, to bounce back on Leah's remark, a more physical energy barrier arises. But we see that it's highly sensitive on theta prime, and we have no way to predict this. So can we still understand why it is going smoothly from this liquid barrier and the solid barrier when we look at elastic gels? And for this, so we can do the same, the side view independent measurement, and measure the contact angle theta. And we see that we have a continuous variation of theta over the ratio between the elastic capillary length over R. So we qualitatively, we also expect an energy barrier that could, we could think that it explains the continuous variation. But there is something that is very puzzling, is that when our droplet nucleate, the radius R is actually nanometric. So in all cases, for all the gels that I use, the ratio between the elastic capillary length with R star is very, very large, even for the stiffer gel that I use. So actually, I do not expect at all any influence of the gel substrate. So this is something that is quite puzzling, and that we still do not really understand. But then we decided to try to look at, try to understand why, first of all, the number of drop plateaus, and whether we can extract the value of this plateau and extract from it some information, some effective energy barrier felt during the nucleation. So to understand the saturation of the number of droplets, what is quite informative is to look at the droplet growth, the later growth, when drops are in the optically visible range. And what we expect actually from the theory is that an isolated drop would grow diffusively. So the radius of the drop would scale as t to the power a half. And in the experiment on the subgel that I use for one given humidity, what I observe is like not a perfectly, I mean, not a beautiful square root exponent. What I see is that I rather have a t to the third trend. And so this actually suggests the existence of interaction between droplets that I will try to explain now. Okay, so in our experiment, we do impose the humidity at the ceiling, and the droplets then nucleate below. They nucleate, and then they grow. And as they grow, they get closer and closer together and start to compete with neighboring droplets to sink the humidity. So using a match asymptotic description of the diffusive problem, we show that n droplets can can build up a boundary layer near the substrate in which the air will be depleted in humidity. So I first solve the outer solution. So I look from far, and at this distance, actually, I can see the droplet as a point sink. And then I use a green function, so the function g, to account for the water absorbed by each punctual droplet. Then I solve the inner solution. So I place myself at the scale of individual drop, and then I write the humidity field around a droplet weighting a substrate with a contact angle theta. And then finally, I match the two solutions. And this actually leads to the humidity that is effectively felt by droplets. It is written here, so rho F. And what is nice in this formula is that you have two limits. So you have a limit for a product RH psi that is smaller than 1. So for which the humidity is almost, the effectively felt humidity is almost the one that you impose at the ceiling. So everything should grow diffusively and without any problem. And then you see that when this product is larger, greater than 1, the effective humidity tends to rotate. And this is dramatic for the condensation, because then it will stop basically condensation. You will not have any more driving forces for condensation. So in my experiment, I can compute the value of this product, and as soon as drop enters the visible range, so as soon as R is on the order of 1 micron, I'm already with, I mean, this product is already about 100. So I only probe the interactive growth region in my experiment. And this explains why the droplets grow subdiffusively with an exponent that is close to T to a third. And we can be actually more quantitative. We can actually plug back this value for rho effective in the mass conservation laws and show that R should actually scale as T divided by the number of drop density psi to the power a third. And in this expression, for example, we can test it for the rigid case because we know the contact angle, theta. And what we see is that, so instead of plotting R as a function of T, I plot the collected volume by converting the radius to a volume using the geometrical function G. So I compute V volume, the collected volume, as a function of the contrast in humidity time T divided by the droplet density. And we see that we get perfect, a very good prediction. There is no adjusting parameter here. The data are well captured by this theory. So now, can we do the same for subgel? So unfortunately for subgel, you're rheologist, so you know that things is much harder. So we know that the contact angle will vary as the radius grow, actually. So as during this dynamics, the growing dynamics, the contact angle will be reshaped. And so the value of G of theta, the function, the geometrical function, will change over time. So we cannot really do it, but what I tried is I gave it a try, and I saw that you could still do it for the early stage of the growth. and get at least a linear trend for the collected volume with our prediction. So perhaps you see in this slide that there are also some data that tends to deviate from this linear trend, and this is actually what happened. The curve start to bend at some point and deviate because the droplets start to sink into the gel, so they somehow collect some of their volume under the substrate. So you can actually see that on this side view experiment. So I'm jetting a droplet with radius 50 micron on a very soft gel. And what you see is that it's really, really slow. It's very, very slowly, but it's sinking into the gel with a slow dynamics. And so this explains why it deviates from this linear trend at a later time. But still, yeah.
Yeah, I do have a question in terms of like technicality. When you can you show again the video? Do you also did you try to eventually reconstruct the stresses around the interface by eventually following the interface? I don't know if you try to do that with the image. I know it's quite difficult sometimes to do that, but
yeah. So I think I mean, we did some trial with some colleagues that were numericists. So they did some FEM simulation to map the stress in the gel. Yeah. And this is very subtle and complex because you have a singularity here.
Yeah.
The stress is actually diverging here. So it's very hard to regularize, but they managed to do it, and actually we have it. But in some sense, we didn't look much into this because at the scale at which droplet nucleate and grow, the droplets are much smaller than the droplets are much smaller than the capillary length.
Okay. Wow. Okay.
So that's why they have this very strange shape actually, because when you have a R that is close to the elastocapillary length, you have a little ridge that is not so much developed. But here the substrate is so much deformable, so that you can really, the drop can really sink into the gel.
Sink into it. Okay. Okay, thank you. Because this would have been so cute to see on the picture, to see how the stresses are going inside and at the singularity, because I know some people are sometimes working on that. There are some people now well, it's not exactly the same thing, but Vincent Bertin is doing some simulation about stuff that are pinching with some singularities, and it's quite interesting. And I thought about that by looking at it, and I don't know if it's the same kind of questions, but
yeah. So I think here what I could do is just to extract the meniscus shape, because it's exponentially decreasing, so we can do such things. At some point, I ordered some polyurethane photoelastic gels, but they were not so soft, so actually I could not have the same deformation. But this is something that would have been cool to have two polarizer and to see
the deformation and so on. Yeah, that is already super cool. You can continue. Sorry. Thank you.
Okay, so we understand better why the droplet grow subdiffusively, because they consume the humidity around them, and so we understand somehow the growth, and now we want to understand a bit more the nucleation rate. And actually, so from Bruno Andreotti's numerics, we learned actually that as soon as we can evaluate at each time step the humidity felt around the droplet, and see how does it modify the growth, but also the number of droplets. Because if you use the classical nucleation theory, you can actually at each time step compute what is the nucleation rate. And what we see here on this left plot is that at t equal about 0.1 in a dimension unit, you see that the humidity is decreased by 1%, and simultaneously you start to enter in the t to the third regime. But also, if you look at the plot psi versus time, you see that you initiate the saturation regime. So as soon as the humidity is slightly decreased, there is a huge influence on the nucleation rate, and this is actually due to the exponential dependence of the nucleation rate with respect to the humidity. Okay, we can actually map in 2D view from the top the humidity, the ISO concentration of humid air around the droplet, and we see that as soon as we cross this regime of interactive growth, the ISO concentration line start to interact and overlap themselves. So not only the humidity consumption slow down the droplet growth, it also modifies completely the energy landscape around the droplets, because in between droplet now the humidity is lower, so the energy barrier to nucleate becomes very large, and the nucleation probability tends to 0. Okay, so what we try to do then is to look at the crossover between these two regimes and to see what we can extract from this crossover as information. And psi naught seems to be selected by this crossover actually between nucleation and the saturation growth. So we know that in the nucleation regime, psi is expected to grow linearly with time, and we will see when this growth is arrested, when this for which time we satisfy this supersaturation condition, RH psi equal to 1. And when we equate these two, we predict that psi naught obeys this scaling, and we can actually try to verify this scaling with our soft gel. So instead of fitting G, I will actually develop the expression of G using the exponential, the Boltzmannian exponential, and I will try to extract from that only the part that depend on the wettability and softness of the gel. So I just put the humidity apart so that I can fit psi naught with respect to the humidity ratio. And what I see is that if I look at the data that I get for different humidity on a soft gel, I get an energy barrier that is really, really much smaller than what is predicted by the CMT, the theory that I presented previously. So it seems that the assumption that drop are microscopic and at equilibrium at this time scale is wrong. We expect actually a scaling up. We expect, depending on the real contact angle that is felt at nucleation, we expect an energy barrier that is about 50 in dimensionless units. No, in energetic unit, sorry, in cavity unit. Okay, so this mismatch suggests that the nucleation pathway where drop a nucleation pathway where drop grow too fast to deform the viscoelastic gel actually. We can also do the same work, the same fitting procedure for the stiff gel. And here it was quite puzzling because you see that the number of drops decreases when we increase the humidity. So when we saw those data, I was really, really desesperated because I thought that we will never understand anything on that and say anything from the energy barrier. But actually, our scaling obtained by looking at the crossover between the nucleation regime and the saturation condition is actually capturing this dependency because you have the humidity dependency on the denominator. Okay, so what we rather did was to, well, what we propose is actually to fit our data to assess what is the effective energy of that is felt during the condensation. Okay, so before concluding, just a quick note on the coarsening late dynamics. So we know from statistical models that coalescence event and Oswald rippling induced a decrease in the droplet number density that follow this scaling in red, written in red. And this scaling is still is verified for the stiff data. And for the soft gel, it can be still verified provided you introduce a delay time, TOPI, whose value is actually plotted in the right, that varies with G, the elastic modulus. So we see that it varies, so it indicates that the delay arises from the viscoelastic nature of the gel, or at least it suggests. And indeed, when you perform the side view independent experiment with a relatively small drop, and you look at their chaos interaction, you can see that the drop will speed up, that those two droplets will interact by through the elastic deformation that they induce at the gel fits. But we see that this interaction will be very slow. So first, it thinks I'm forced to speed up this movie because it's 5 minutes long. So you see that it's first the drop first sink into the gel, then they start to attract themselves, and eventually, after 5 minutes, so 5 long minutes, they come into contact and merge quasi-instantaneously. Okay, so this delay is actually we think that it's due to the viscoelastic properties of the gel, and which is quite interesting because it can really stop the nucleation, the condensation process. And so in the perspective of making some patterned substrate where you have a high monodispersity, you can think as a strategy to use viscoelastic polymer films. Okay, so then as a conclusion, so we see that nucleation, random nucleation at least, sees when a saturated diffusive boundary layer builds up above the substrate. We have seen that the late coarsening obeys the universal law, provided you add you take into account the viscoelastic nature of the gel. So condensation on subgel exhibits, the breadth figure exhibit a nearly modisperse distribution even at a later stage, which actually contrasts with most of the breadth figure reported in the literature. And the way we understand that is that there are actually 3 ingredients to achieve monodisperse patterns. So the first is to have, to nucleate on smooth substrates, because otherwise you will nucleate on defect constantly. As soon as you free a defect, you will nucleate on it again and again. And then second thing, you need to operate in a diffusive regime for the air. So this works when you prevent convection in your cell. So if you blow on your humidity chamber with a too high flow rates, then you will refresh this diffusive layer close to the substrate. But also if you tilt or put up, you return your setup, then the vapor you will have natural convection that will prevent this diffusion control regime to set up. Last ingredient is actually to inhibit coalescence at later stage, because otherwise you will have a droplet that will have a larger volume, so larger size. So the main unexplained observation in our experiment is that tuning the cross-linking density of our gel, the surface density of the dew droplet seems strongly affected, and this is something that we still do not understand, which is not captured with microscopic theory. So once more, the classical nucleation theory is qualitatively okay, but not quantitative. And those observations suggest that nucleation occurs via a macroscopic path with a lower energy barrier, which seems sensitive to the degree of reticulation. So at some point, we were thinking that there is probably a kind of crust at the surface of the gel, or at least that the molecular state of the surface of the gel is different than from the bulk, the one that we probe with conventional rheology. And if it's true, actually, the nucleation experiment or condensation experiment can be a way to probe the surface state of a polymeric interface and the surface energy, whether there is a crust, bending air, ends, or if it's a liquid. And with this, I just thank you for your attention, and we'll be happy to answer your questions.
Thank you. Thank you so much. It was really, really nice. And you have very nice experiments. It's very beautiful. Does anybody have questions from the audience? I don't see raised
You can
hands.
also write in the chat if you want.
Yeah.
That's okay. Don't be shy. I just received the text, I must say, because no one wrote it in the chat, but I just received the text that was written, "The pictures are so beautiful," from the person in the audience that is not speaking right now. But
thank you.
yeah, I must say it's also beautiful. But behind that, I have also some questions. The last video where you have your two droplets that are coalescing, it's quite interesting. And I was wondering if you were trying to relate the time it takes to coalesce with some relaxation times, because there are different relaxation times of viscoelastic fluids, but does it collide with some certain relaxation time of this soft gel or
Yes,
not?
a very good question. So I think probably the answer is in the paper from Stefan Karpichka and where like postdoc with Jakos Neuer, where they look at a Carius interaction between droplets. So it's inverted Carius. Do you know what is Carius effect?
No.
Okay.
Sorry. I'm here to learn stuff. Tell me.
No, I think you probably know it without knowing the name, but so when you have cereals that float on your milk in the morning, they tend to interact through their meniscus. So the meniscus makes some slopes, and they just minimize their energy by getting into contact. And here, what the Jakos Neuer did, I don't know, 8 years ago, something like this. They looked at the inverted Carius effect. So why inverted? It's just because you invert the phase. So normally it's a solid floating on liquid, and there it's a liquid, liquid droplet floating on a gel. And because they form those menisci, they can actually interact. They do the same. They feel the same attractive force. They get in contact and finally merge. And the delay for merging has not really been studied, because what Jaco were doing, it was doing a sliding experiment. So two droplets sliding on a vertical soft cells, and they were coming into contact.
Yeah.
But it was night experiment. It was not it was super slow. And here I think it's a good question, because I have a few data for different gels. And I also have a top view where you look at very tiny droplets, two droplets, and you will see that actually this two droplets feel an attractive force each other. I'm speeding up the movie because it's 5 minutes still. And so you see that they somehow deform and lose their circular shape. Because there is this attractive force that is exponentially decreasing with the spacing between the two objects. So it's highly, it's very intense in the center and less pronounced on the edge. So you really deform your droplet because of that.
Because the energy it takes to deform a droplet that small, it's a lot, because you have a lot of capillarity. And also you cannot think about that effect with just a lubricating thing. It's not a liquid inside, it's a soft gel that is viscoelastic. So maybe it's eventually really like linked with the rheology, and as you deform it, maybe at the center where you have a very high pressure, you're gonna crack it.
Yeah, it's a very, very good point. I think so. The only thing, oops, the only thing that I can say. So I think my screen is frozen. I think this value here, TOPI, the delay for the merging the coarsening to start, the coarsening phase to start, TOPI is actually reflecting this delay. I had plotted at some point the value that I was adjusting from this fit, and the value that I can measure on independent measurement.
Yeah.
The much less point for independent measurement, but they were very similar. So I think this value TOPI that is plotted here is a reflect on. So it depends on G, and it depends on G on a non-trivial way.
Yeah,
so I think from if I remember well, it's a power a third minus a third.
Okay.
So it was quite puzzling, and this could, at some point, I wanted to compare it to the rheology curve that I got for the different gels. So this is the G, N, and the relaxation time measured for the different ratio of the gels that I prepared.
Okay.
And you see that the relaxation time is supposed to be inversely proportional with G. And the TOPI that I was measuring is like scaling with G to the power minus a third. No.
Okay. Interesting.
Some rheologists know what to say about it. Probably some geometrical effects because you have a gap that is, but I don't know. To be
thin. Because sometimes you have when you think about the Poiseuille law inside the confinement effect, you will have some aspect ratio that's going to scale to the power of 2.
Yeah.
And I don't know where is the minus 1/3. I have no idea.
No, but it's a good. I tried to do it with viscous oil because I had no. Because there were nothing done with Keros interaction on highly viscous liquid. So this is a project that is ongoing actually with a very nice student. So he's looking at the interaction of two solid particles on a highly viscous liquid. And you see that you start with a very common capillary-driven phase for the dynamics. But then as soon as you get the two objects get closer and closer, then you have energy. You need some energy to evacuate the lubricated layer. And this is super long. This is like our experiment as well.
Okay. Who is he? The student that is working on that?
So he's a L3, so bachelor student, Martin Trébeau, who is from ENS.
Okay.
Months ago, but collecting already tons of data.
Okay. So yeah, I'm gonna follow his work. Very nice. Thank you.
Person,
yeah. Maybe I'm a bit monopolizing the questions here because I really kind of subject because I like viscoelastic fluid because I'm working on that and some cavities that are merging and stuff like that. But it's not at all that. But if some people have questions in the chat, you can, or you can also maybe send a little email to Ambre if you have some questions. Or I saw also nothing to do with this talk, but we also have some questions in the comments or in YouTube. So for people on YouTube, you can ask questions in the comments and maybe we can send it to Ambre.
Yeah.
So, yeah. So go ahead if you have any questions, Nicolas, José, Achif, or Marion, or maybe Michel. I'm sorry, maybe.
Maybe just a naive question from the video you from the top view of the two drops coalescing. I was just it's also curious the shape it gets after yeah, and is it actually gonna become again a circle or how long is it gonna take?
Let me, okay. It's gonna, I mean, it takes quite a lot of time. It's easier
It's
on top view. It's very long to relax actually. So you see, well, I had to stop it's under the microscope. So when you stop, you in just turbulence, not turbulence, but then what you see is that the shaded region here is the ridge, actually the information that the droplet carries with it. And once you merge, so the merging is quite fast initially, so it zips the bridge. You still see the deformation here that will dissipate, but on a longer time scale. And then you also see that it took some time to reestablish the meniscus, the meniscus or elastically capillary ridge around this dipole, merged dipole. And I actually didn't wait until didn't wait enough to see the full relaxation to a circular shape. Maybe on the condensation case, I think I had at some point, if you zoom really carefully and look carefully, you see that some of the drops will not keep their spherical shape. But I was taking picture every 5 seconds, so I think I could not really. It was taking very rapidly its equilibrium shape.
Very, very curious. Very nice. Thank you. Thank you again.
So I think that there is question in the chat, but I cannot see the.
Oh, just somebody saying, Marion saying thank you to you and
okay.
saying bye. Yeah.
Thank you for attending.
Yeah, thank you very much. That's very interesting.
So I guess we can stop the recording here.